Okay, so finally I settle into solving this problem and being able to give you something that is clean in this part that I wanted to discuss now. So I will begin by quickly noting just an aspect from last time, and then I'll move on to something different. Remember that there is a chi-squared distribution right? And that the chi-square distribution comes from the summation of the squares of a Gaussian with zero mean and unit standard deviation, right? So if we have, just to remind you, if we have a Gaussian distribution, I'm going to do it with a single variable. If we have a Gaussian distribution where the mean is 0 and the standard deviation is 1, and this is x, and this is the PDF, and if we sample that distribution and we obtain x1, x2, etc., up to xn, right, where n is a large number, and we calculate something like, let's say, z to be the summation of xj squared from j equals 1 to n, then z for large n, right, is chi-squared distributed. Okay? So the chi-square distribution is the sum of the squares of a Gaussian, with unit standard deviation. All right. Now, if we have a Gaussian with unit standard deviation with a non-zero mean, let's say a mean x bar, right? So this is the same distribution, just shifted somewhere else from 0. If we have a distribution with non-zero mean and unit standard deviation, and we sample from there x1, x2, x3, xn, right? And so on for large n, and we define z again. Well, let me not just call it z, let me just call it g. So if we define g as the summation from j1 to n of the xj squares from there, then g is non-central chi-square distributed non-central chi-square distributed, and the non-centrality with a non-centrality parameter which is lambda, which is the square of x bar. Okay? That is the real fundamental chi-square, right? Chi-square distribution with zero mean, chi-square distribution with non-zero mean. Okay. Now, let's continue onward with this real basic situation, and then let's see, I mean, this is nothing new from what I've talked before, but in fact I am kind of walking backwards, if you'd like. I presented the material in a little bit more of a general manner, going to vectors right away, and now I am stepping back and just giving you another look, but from a really, maybe a second look, right? From a more simple perspective that may help solidify or clarify some things. So now we're going to assume, let's say that we have a single degree of freedom system, right? So it's a single degree of freedom system, which we could show like this: mass, stiffness, damping, or we could show it as a one-story shear building or something like that, you know, whatever. That system will have a certain frequency, let's say omega, right, in the undamaged state. But when we identify this frequency in the undamaged state from data, that is, we observe data and we perform system identification, maybe with known input or with unknown input, due to the fact that there is noise in the measurements, right? And that, well, two cases, right? If we had the input, if we have input output data, as we've had in some homeworks, then why is it that we cannot get omega u exactly? I mean, academically we can, but why can't we get it exactly in practice? Because what we have is really not the, is not, because what we have is input plus noise and output plus noise, right? So we don't really have the input and the output, we have input plus noise, output plus noise. And since the noise differs every time we do the experiment, what we calculate for omega u is a different value every time. And therefore, Wu is a random variable, right? So if we perform the experiment 1,000,000 times, we would have, depending on the level of the noise and so on, some sort of a distribution that is very likely to approach a Gaussian distribution that would look something like that. So if the procedure that we are using to estimate the frequency, let's say our identification method, is unbiased, then the mean of the distribution would coincide with the correct value. Of course, we are talking here about conceptual issues, right? Because in reality, we can't do the experiment 1,000,000 times. We're only probably going to do the experiment one time. And so when we do the experiment one time, what is it that we actually obtain? We obtain one value from this distribution which is hidden somewhere, right? It's not something that we can see. It's hidden somewhere and we just looked at one value. Okay, but anyway, we cannot get, my point is that omega u is not a number, it's a number in some sort of idealized space of noiseless data, or in the space of the true properties of the system, but in reality, no. In reality, when we test for it, all we can observe is a realization from a distribution. Now, if we only had, if instead of having input-output, we had only output, if we have output only, then of course the frequency that we will identify will also be a random variable, right? And if the distribution is if the method is unbiased that we use, it would still have the correct mean in that space that we don't have access to, but the standard deviation would tend to be larger. Why? because here we don't have input plus noise. We only have output plus noise, right? But we also have assumptions in which the derivation is based. What are those assumptions? We assume that the input that we don't measure is stationary and white. That it has all the frequencies and is stationary. We assume this, right? The real input will not be perfectly stationary and will certainly be not perfectly white, right? In addition to that, we assume that the signals approach a duration equal to infinity, right? In other words, we have very long signals, so expectation are accurate. In reality, we have signals that can be long, but certainly we cannot do practically a test and wait, a week measuring data, due to space and due to the fact that the improvement in accuracy that you're going to realize is not proportional to the effort. Therefore, we will accept the fact that whether we have input and output or we have output only, when we do a test and we perform system identification, and I'm keeping it here in the simplest case of a single degree of freedom system, we will obtain some value, this one, some value, that one, I'm sorry, this one, right, from that test, anyone, that that is from a distribution that depends on the noise, on the realization of the moment. Okay, now, in the case of a single degree of freedom system, the chi-square distribution would not be necessary. We could just simply work with the Gaussian. But when it goes to the multi-degree of freedom system, or I shouldn't say multi-degree, when it goes, because I could have a multi-degree of freedom system and have only one frequency, the argument would be the same. What I mean to say is here is consider the situation where you don't have just one frequency, but you have, let's say, 2 or 3 or 4 or 5, right? So in the case of multi, whether the identification has provided us with multiple frequencies, then dealing with the multivariate Gaussian distribution directly is unwieldy. It's not, we don't have the exact expressions for what's going on under the thing on a multivariate Gaussian, so we rely on the chi-squared, which brings the process back to scalar. The price that we pay in doing that is that in the case of the Gaussian itself, we can restrict our tests to one-sided, because we can say we are interested in looking for damage for values of the frequency that appear to be too small. We don't care about values of the frequencies that appear to be too large, because if they do, they're just kind of freaky values. They really are not reflecting damage, right? When we go to chi-squared, we are squaring the measurements, and therefore we no longer have a sense of the position that they have. I mean, we square the measurement minus the mean or something, so we don't know which side of the distribution they are. But that is a price that is certainly worth paying for the convenience that we obtain as a result. So let me then go to the chi-squared and say, okay, we're going to go to the chi-squared even though we're going to stay with a single degree of freedom system. I mean, I keep saying single degree of freedom system. Even though we're going to stay with a single frequency. Okay, so we have a single frequency. Now, we have a single frequency, and we begin, this is time, and we begin testing here. And so during this time, we are training. So during this time, we measured, before I said we would measure it only once. That is really not correct. Maybe we measure it once when we're testing for damage. But in order for us to have some idea about the distribution, we need to perform a number of tests during some time in which the structure is known to be in the reference state. Okay? Some people like to call it on damage. We could call it on damage also, but it doesn't really matter whether it is damage or undamaged. I mean, all we're saying is that's our reference. The way the structure is now, that's our reference. So we obtain enough data here. Well, not enough, some amount of data, right? Probably that data is not sufficient for us to say, let's compute the distribution by simply observing the data, because the data is kind of still probably reasonably small in number. But if we make the assumption that the data was distributed in a Gaussian, then we certainly can calculate the mean of the distribution, right? And the standard deviation of the distribution. We made the assumption, take that back, wait, this is not in the right order. Let's be more precise. From the training data, no matter what the distribution, this is the way I should say it, we can always take whatever data we have and we can calculate the mean, right? So the mean is just simply the summation of all the undamaged j's measured, right? From j equal to 1 to the number of training points that we have, right? Times 1 over the number of training points. So if we do that, we can, that is the mean by definition, right? The summation. And we can calculate the standard deviation as the summation of WUJ, right? Minus the mean squared, right? From j equals 1 to the NTP, and then take the square root of that, right? And then times 1 over n. Okay? So we take the difference between the samples and the mean, square it, add them all together, take the square root, take the average of that, that's the standard deviation. Now, the mean and the standard deviation of a set of data exist and are given by those expressions. They do not indicate that the distribution is Gaussian or not. They're just the mean and the standard deviation of the data. Now, if we assume that this data is Gaussian, then those two numbers are all we need in order to fully sketch the distribution, because the distribution is exclusively dependent on the mean and the standard deviation. If we were to make an assumption for a different distribution, it would require other parameters perhaps sometimes. But that's not our case right now. We're just simply stating that with those two parameters, here is our distribution, right? Now, let's see. Once we have that is the distribution, we can certainly say that the variable z let's see, do I need to explicitly state it or not? No. In this case, our chi-squared, we are simply saying, we are saying that our variable z, which would be given by our whatever frequencies we measure, right, minus this mean frequency, right, divided by the standard deviation and squared is chi-squared, right? So I don't need really to actually, let's see. Well, I think it'll be clear. So we know that that is chi-squared. Now, the important point is this now. So if we now look at a chi-square distribution with 1 degree of freedom and central, right, because this is central, we find that our chi-squared that is central with 1 degree of freedom or something has a distribution, let's say something like that. Actually, no, that's not true. That's not true. Something like this for PDF, I think. Yeah. This is this would be omega, and this is the PDF. So this would be the chi-squared with 1 degree of freedom. Now, I shouldn't say omega, I should say z, right? So that's the PDF of the chi-squared. Now, if we want to classify something as being damaged, we will say, okay, the probability that z is larger than this value is whatever we choose that area to be, right? So if we choose this to be the type 1, recognizing that we have the error on the issue of the tail, but if we choose that to be type 1, and we typically would take this to be, let's say, 0.05, then we can actually read what is the SZ. And the Z critical, as I think we've mentioned now in previous classes a couple of times, this would be what? This would be chi-squared inverse, right, in MATLAB, chi-squared inverse, no, is this the chi-squared inverse? Wait a second. Yes, chi-squared inverse, this would be here 1 minus the type 1, right, which, not 0.95 for example, and the number of degrees of freedom, which in this case would be 1. So I guess what I was hesitating a few seconds ago is that notice that this computation here has nothing to do with the data, right? We could do that even before we do anything. That is, the critical cut for the chi-squared, if I want that type 1 and I had only one frequency, would be this number. That has nothing to do with whatever I measure. Okay? That's something you can calculate from the get-go. That ZZ is a number. You could set it from the outset. Now, once you have that ZZ, or you could calculate it from the beginning, you are now continuing and you say, okay, let's say this is our test time. So testing. So now when we obtain a value here, right, of the frequency, then what we do is what? We have that, let's say, omega j, right? So we say the z corresponding to that value under the null hypothesis. What does it mean under the null hypothesis? Under the premise that there is no damage, that's what the null hypothesis means. Under the premise that there is no damage, the mean from where this was coming is the same as before. So this would be like that. We made the assumption that the standard deviation does not change as a result of damage, and so we find our zj squared, our zj to be simply whatever we measured minus omega mean over sigma squared, right? And we get a number. And then we just simply ask ourselves, how does zj compare to zz, right? If zj is greater than zz, we announce damage. That was the very first thing that I covered, so I just repeated it for you, right? If zz obviously is less than, then we don't announce damage. Why? What happens is, in this case, we have no idea about what is the distribution after damage. We are just simply saying, does this number look like it's coming from the undamaged case? So we subtract the mean, look at it and say, okay, it doesn't look like it does look or it doesn't look like it's coming, with that kind of a confidence, right? That kind of is the simplest version of our point-in-time detection. That is, we don't here attempt to calculate, to use information as it accumulates. We're just using one value, right? Now, when we have multiple values, right? Not multiple values. If we want to do not damage detection, but change detection, right? In the case of change detection, we attempt to use the information as it accumulates through time. And in the last time, I gave you a summary in the last lecture of the change detection with the formula for omega n, if I remember, right? Now, in that case, what we do is we test. I don't want to put the formulas here because when I was preparing the lecture, I didn't think of doing this part, and it just sort of came out as I was talking, but let me just say this. We have what we do in the likelihood ratio test, like the likelihood ratio test is we say, all right, there is a chi-square distribution which is central, okay? And there is a chi-square distribution that is non-central. We associate the chi distribution that is central with no damage. And we associate the chi-square non-central with damage. Now, the chi-square distribution that is non-central requires a non-centrality parameter, lambda. So in the likelihood ratio test, please go back to the previous lecture to review it, but in the likelihood ratio test, we operate with the log of the likelihoods, and we have a set of data. I'll just put it informally here. We have a set of data, right? A number of measurements, and we calculate the likelihood of that data, and the likelihood of that data we calculate it under two hypotheses. We calculate it under the hypothesis that that data is coming from a non-central chi-squared, And so that is likelihood 1. Likelihood of non-central, I'll write it like that, instead of with equations. And the likelihood of central. And we basically just try to see if which one of the two likelihoods is higher, right? We take the log eventually of this and go like that, right? But for convenience. So if the likelihood that is non-central is higher, then this number tends to be bigger than 1. And when we take the log, we get a positive. And when the non-central tends to be smaller, then this number is less than 1, and we take the log of the ratio, we get negative. And so that's how the thing gets detected. Now, in all this procedure, and as I described before, and this is the whole, this is the reason for this sort of repetition, there is this non-centrality parameter. And 10 minutes ago, I said that the non-centrality parameter is just what? It's just the mean squared in the case of a single variable, right? Now, do you know what the mean is after damage? You don't. So in reality, you do not know the non-centrality parameter, right? But I want to make the point here as to at least bring out the correction, because I didn't write this correctly last time for you guys, I don't think. What is the true non-centrality? It's not that we can calculate it, but it is appropriate to know that if you go through the derivation, you will find that the true non-centrality parameter is the mean of the undamaged distribution. That's a vector, right? Because we're dealing with a multivariate case. Minus the mean after damage, transpose, times the inverse of the covariance, times the mean minus the mean again. This is a scalar because that's a vector horizontal times a matrix times a vector on the vertical, a column vector. And so that is the true non-centrality. The reason why we cannot compute it exactly in practice is because we don't know what is the mean of the damage distribution, right? We don't have the damage distribution. We only have this one. Therefore, in order for us to estimate the non-centrality, we have to make an assumption on xd. Now, you're going to say, but how am I going to guess that? Well, you don't really need to guess it correctly, because all we are trying to do is to determine if it's more likely that the distribution, if the distribution 1 is more likely than the distribution 0, right? So if the damage reduces the frequencies, right? And we assume, let's say that the non-centrality parameter true one was 3, and we assume 1. That doesn't mean that we're going to get the wrong answer, because the non-centrality 1 is still better than 0 once the structure gets damaged, okay? If we actually had the exact non-centrality, then the test would be as sharp as possible, the likelihood ratio test. But we don't really need to know it. We can take any guess, and the only thing you cannot do is make a guess here which is so wild big that, let's say, you know, the non-centrality for no damage is 0, right? Let's say that the true non-centrality that we don't know, but let's say that the true was 3, right? Now, if you were to guess point, your guess could be 0.2, 0.3, 0.5, 1, 1.5, 2, 2.3, 3.1, 3.6. All of those are going to work, okay? All will work, because all of these non-centralities are going to show that the data is more likely to come from there than to come from 0. However, if you said that your guess for the non-centrality is 55, then the procedure is going to say, no, 0 is better than 55, right? So the point is that your non-centrality guess should err on the shorts, on the small side, right, of the true non-centrality. And there is no need to err by a little bit. You can err by quite a bit, right? And you could even err going on the other side, because 3.3 would still work, but you cannot do something like this, right? Because if your non-centrality is just 3 and you assume 55, the data for lambda 0 would be more like. Okay? Okay, so I just wanted to point out, for when we get to this subject, examples or application in a little project or something that I have to contrive for you guys, that you have clear access to the fact that the non-centrality parameter correctly is given by the formula that I just placed. So you can make yourself some reasonable estimate of what you would like to assume when you do the likelihood ratio test. Okay? Fine. So, what I'm going to do now is to rewind a little. That is, I'm going to go back to a fundamental question that we haven't addressed, which is, how is it that we can discriminate when we do identification under noise, and the singular values are not going to be so nice as what you saw when you were doing your previous homeworks or the model updating challenge, in which case there is no noise, the input and the output are perfect, and there is no question. You see a humongous gap between the singular values that tell you what is the order of the system and the rest that have to do simply with round off and finite precision arithmetic in the computer. In homework number 9 or 8, one of the two, I don't know, I guess 9, you already have a case where a signal has 3 rows, that is, we're measuring 3 things, and you don't really know what the system is. So you don't know if those 3 measurements were taken from a system that had 3 degrees of freedom, 6 degrees of freedom, 9 degrees of freedom, or 100 degrees of freedom. You don't know, because all I gave you were the 3 signals. That is realistic, right? In reality, those 3 signals could have been coming from, I don't know, the wing of the space shuttle days before, or the wing of an airplane, or a wind generator, wind tower, you know, whatever. It's not obvious, it's not like a sheer building, oh, I just count the levels. So all you have is these signals, these 3 signals. And you want to do system identification to see what you can learn about this structure. Even in your homework 8 or 9, when you do that, there is not going to be any big hole on the singular value plot, because in the case of output only, you don't even need to add noise to the situation. Just the fact that the process is not infinitely long, as it's necessary for it to satisfy the expectation values being correct will already kind of throw a wrench in the situation and you will not see a huge hole. Let's just say then that the issue of deciding when you're doing identification what is a result that represents the real system and what is a result that has nothing to do with the physical system, it is what we refer to as a computational mode, is a long-standing problem to which a lot has been written and which we know how to do something about it, but it's not an issue that you say, oh, there is a solution like this, magic bullet, do this and that's it. No. All we can say is, well, this is as good as we can do. We do this and this and this, which I will give you now, and that's how we try to tell them apart. Now, notice this. Notice the following. Why we have computational modes. And by computational modes, I mean natural frequencies and mode shapes which are not really from the system. They are from the math only. Because in reality, we have input, right? And we have output. And if this output was the result of that input, I'm treating the simple case of input-output. If we had an input, and that input gives me this output, I can do ID, right, and find omega, which is, let's say, the real system, with frequencies, whatever. Let's say the data that you use for the model updating challenge, right? There was input, there was output, they were not contaminated. You run the ID, you find two frequencies, they are correct. In reality, what's the situation? You have input plus noise, right? And you have output plus noise. So the system identification doesn't know. It just simply says input plus noise, output plus noise, that's just input and output, right? And then it says, okay, what is the system that connects these two things? And you find this, let's say, gamma with the bar, right? Which is not this one, because this one maps the input to the output. This one maps the input plus noise plus the output plus noise. So it turns out that in this system, let's say that this was the updating challenge, you had two frequencies, omega 1 and omega 2, right? That was enough. The thing matched it perfectly. But now, if it's input plus noise and output plus noise, maybe the system identification, which will not show two clear singular values, might give you omega 1 bar, omega 2 bar, omega 3 bar, and omega 4 bar, and you're not sure if those things are all from the real system, which one of them are good, and so on, right? So this is the question that we face. Why? Because of the noise. How to separate it is what I'm going to try to talk about. And as I said, I'm not going to give you a magic bullet that says, oh yeah, oh this one's this one and this one is correct. No, but I'll give you something that will be the state of the art basically on how we attempt to make this distinction. Okay? Let me pause it here just for keeping the file sizes short.